Hello and welcome back. While the audio PCB is being fabricated and assembled by PCBWay, I wanted to talk a little bit about the process of how to get to this audio board being created in the first place. So I was working on this video hardware and I was thinking about how I wanted to have a fully featured demo of not just video hardware but also nice audio. So I knew that I wanted to have audio which was roughly comparable to what I would expect to see from the old Amiga days. This means that I wanted to have, say, 4 channels of stereo audio with PCM sound capability, with the ability to set an optional loop and also some independent volume settings for each channel. So I was experimenting with various different memory layouts and came up with this kind of design for the internal sound registers. The first byte is volume. It then has a start address for the sampled audio inside the audio hardware's memory. This is a 16-bit address, low and high bytes. I don't really want to have more than 64 gigabytes of memory on the audio card because that would start really getting quite insane with through-hole 5-volt parts. Then there is the length of the initial sample to play in terms of bytes. Then there is a rate. Now, this rate, to allow the hardware to play various different pitches, has to have some degree of accuracy attached to it. So actually, the accuracy is about 12 bits. This is why we've got a 16-bit value to allow us to play faster or much slower than the target output sample rate. The target output sample rate for this hardware is actually 25 kilohertz, which gives us a nice range of pitches that we can play back samples at. The rate can be calculated by taking the original 4 megahertz clock. So taking the frequency in hertz, multiplying it by 496, and then dividing it by 25,000. And then that's the value which goes into the rate here. This allows the frequency in hertz to be easily convertible from various different input sources. Then we have an optional loop address and loop length. This is to allow repeated samples, obviously, some kind of extra musical effects that can be utilized. And to be honest, the looping capability is really quite important for a lot of the original Amiga mod files or the tracker files that are very, very commonly found. So this was the original register design. Now, like the scale sprites, what I did was that I started prototyping the hardware in terms of Java code inside the emulation framework that I built up, which also includes all of the video framework. So what this means is that, first of all, during the write data for the internal memory bus, I had to start intercepting all of the writes for the volume, voice address, low and high, the voice length, low and high, the rate, low and high, loop address, loop length, low and high values, but also the writes for the looping for each voice. So there are 4 voices and there's a bit for each voice in this byte. And then there is a voices active mask. Now the Java code is quite flexible. So as well as having a size for the voice bytes, which is 11 bytes per voice, there's a concept of having a different number of voices here. Now, when I was working on the hardware, I discovered that 8 voices was going to be very hardware intensive. I mean, 4 voices is relatively hardware intensive, but 8 is even more so. So I downscaled it, if you like, down to 4 voices. And that's for the register interception. And then actually the logic for calculating the samples in terms of Java code is actually really quite simple. This method here, calculate balanced samples, is called twice. Once the channel sample buffer has some space. So it goes if there's no available space, it returns. If there is available space, it calculate some samples to try and fill that space. And this means that when the samples are playing in the emulation, it would just fill the sample. So the logic is actually really quite simple. It looks at the voice's active mask for the current voice that you're currently trying to process. It looks to see if you are currently looping or not, and if you're looping, it selects. If the internal state is currently looping, then it chooses the address to start reading the sample from the loop address. If it's not looping, it chooses the original voice address as the start address to start calculating sample reads from. It then adds on, of course, the internal counter, and the internal counter starts at 0, so it just basically doesn't add internally. And then it starts reading the sample RAM. It does some rebasing arithmetic here to rebase the sample to a signed integer. In hardware, this is implemented differently, but what it does is that it does a multiply by the volume, and then all it does is then accumulate this volume altered sample into the accumulated sample, and then the accumulated sample is clipped so that the values don't go out of range right at the end, and then the sample buffer gets the result of the accumulated sample. But after calculating the accumulated sample, there is the extra logic here to do with whether or not you are looping. If you're looping, then of course the internal counter is compared with the voice loop length, and if it's more than the voice loop length, then it resets it to 0. If it's not currently looping, then it does this comparison, which is the original voice length. So the original length of the sample can be different to the looped length of the sample. And if we've got looping enabled, then it chooses the internal, it basically sets up the internal state to actually start choosing the loop length and the loop address. And it will reset the count to 0. Otherwise, it turns off the active voice. If it's not looping, when it reaches the end of the sample length, it turns off the active voice. And that's just basically all this does, and it does this for all of the different voices. Now, in Java code, it's actually really simple. So then, once I wrote the code, of course, I needed to test it in the rest of the emulation framework. And so there was this little original demonstration which combines all of the video hardware along with a sample, which optionally loops on one of the other channels. And this exercises all of the code interfaces and all of the memory bus interfaces. And we should get a sample playing now. Now, of course, because I'm recording, actually the emulation is not running that quickly when it's recording. Without the recording, the emulation is actually a lot better, but you can hear a broken sample in the background there. So I'll close, well, the window's closed because it's reached the end of the test. And the test was basically this. It sets up all of the extra hardware and everything else like that up here, of course, and we've got the new audio expansion hardware initialized here. But right down at the bottom, what it does is that it calls play sample, and play sample itself is here. And what play sample does is it just sets up the address bus to turn off here. The address is here, 802C, which is inside the audio hardware, and then it just basically turns off the voices. It then starts with the first voice data, and then it starts outputting volume, start address, length, rate, and so on and so forth. And then at the end, it initializes the voice, which should start it playing and looping. Okay, so that's the code that it was running, and then we heard the results. Then what I did was that once that was working in emulation, I then moved on to doing a little bit of a better test, because I really wanted to test out the proposed audio hardware design with some better data than just some sample that I had lying around, probably from Dragon's Lair. the arcade game, if I remember correctly. Anyway, so this test combines the audio from an Amiga mod file. So the mod file was chosen to have a wide variety of sound effects. It's running a little bit slowly because I'm recording while it's emulating. This plays at full speed when I'm not recording, of course. So this mod file has a good selection of samples. It has looping and non-looping sound effects samples, and it has the samples played at a wide variety of different pitches, so that I can hear if, when I run this test, because the test is configured to output debug data, the debug data will actually tell me the debug data is here inside video hardware, inside the target directory. The test is actually configured to output this debug data text file. This debug data text file, if we open it, will contain all of the memory bus writes which go out through to the video hardware. And we actually here have, on different frames, we have some of the frames outputting control to the audio hardware. So if I look for that, for example, here, these are writes to the audio hardware control registers. So we can see here that the voice is being turned off, and then we're editing some of the voice parameters, and then we're turning the voice back on again for playing the first sample with maximum volume and a different memory address and all sorts of different looping parameters. And so this captured memory debug can then be used inside the hardware when I'm actually trying to spec out the hardware. So now what we have is that we have the Proteus design tool with the loaded audio schematic. Now this is the first sheet, and if we have a look at the virtual data device here, if I open up the properties, then we can see that the pattern file being used is the debug data, which was output from the video hardware, from the demonstration that had just been running. This debug data is not edited in any way, it just comes straight from the emulation. This allows us to then start working with the data that we see from the emulation to test to make sure that everything can be written into the RAM correctly, and all of the registers and sound and voices, audio voices, they behave as we would expect. Now this first sheet doesn't have much on it. What it does have is that it has this little circuit here, which just basically is not part of the audio card, but what it does is that it just exposes the expected extension memory bus access lines for the different parts of the address space, with EBS 0 set to be 1, which allows us to intercept the correct memory address. And what we're going to be doing is that we're going to be using the audio registers for this. Now, also up here in the top left-hand corner, what we do have is that we have an audio clock set up to provide a 4 megahertz audio clock. Now, this is quite quickly divided down. So the audio clock here goes into this 7474 here, which very quickly divides it into a positive and negative 2 megahertz signal. This signal then goes down. This is the header sheet, so that we can actually plug the board into the backplane. And this clock signal here quite quickly gets divided down even further, so the 2 megahertz input here gets divided by 4. And then basically the audio processing hardware is a very large finite state machine. So the audio hardware has several well-defined states. We can see here that we have, let's zoom in a little bit, we can see that 4 voices are actually processed in sequence. So it outputs the address. It outputs the address again and does some extra processing. It reads the RAM, then adds the counters, and then it compares length and does all of the logic that you would normally expect for doing the length comparison, the loop comparison, and so on and so forth. And these 1, 2, 3, 4, 5 states are repeated for the other 3 voices until we get right down to this end state here, which resets these internal counters, and then it loops around back to the first state again. We actually have 20 states because this is an asynchronous clear going into the 74 161s. So what this means is that in real terms, the first state here is a tiny little bit, about 50 nanoseconds or so, shorter than all of the other states. But to be honest, we are talking in the region of 2000 nanoseconds for each of these state transitions. So we're really not too worried. You know, this is audio hardware, and audio hardware doesn't have to run as fast as the video hardware does, thankfully. So this is the clock to internal state triggering circuitry. Up here in the top left, we have the address decoding for all of the registers. Now, remember it was 11 bytes, I think it was, for each voice. So don't forget we have 11 bytes for each voice, and we have 4 voices, so that's 44 bytes, plus a couple of extra bytes for the loop mask and the active mask. So actually we have a lot of internal memory decoding for all of these registers here. Now, all of these registers map to the voice-specific registers, and most of these are 8-bit matches. Okay, we're not using RAM. We want to vastly simplify the access to the sample register memory, so using a large amount of latches makes sense rather than trying to figure out all of the memory access logic. So this is the address decoding logic here. This is just a little capture of the output data. So this is set up to actually capture to a debug audio output file, and for every load output, which is at 25 kilohertz or 25,000 hertz, load output is triggered, and this just outputs the debug. But load output is also used to load the final value for the 2 stereo channels into the final output drivers. We'll get onto that in a second, but this is just basically allowing me to trap, for debug purposes, all of the data that's being calculated, the digital channel data, the first channel and first channel, second channel. Okay. This one here allows me to capture more detailed internal state for when I was actually debugging this. So the common read address, the sample data output, and all of that kind of stuff, which was kind of useful. The next part of the common circuitry is this computer circuitry here. So these are basically a bunch of adders. Oops, bunch of adders here. These ones here. The selection tool is not working. Okay, here we go. These are a bunch of adders which take the common address and the common position and then output a common read address. Now, for each of the voices, because the voices go in sequence, the voices, only one voice at a time accesses the common read address, and the common position is basically outputting it onto a common bus. And then this adder will get that information discretely for each voice and do the calculation discretely for each voice. This common read address, of course, then goes into the common read address selector here. Now, this is the internal or external memory bus selection logic. So if you're writing to the sample memory, it will select it from the external memory bus. Otherwise, it will use the internal memory bus common read address, and it will select that appropriately. Now, because we have 64 kilobytes of memory, then of course we have 8 kilobyte RAM chips, static RAM chips here with appropriate bus isolation for each RAM chip to avoid all of the contention issues and stuff like that that could arise out of having a common internal bus attached for each of the memory chips. And then this just basically allows us to write sample memory, but also read sample memory according to the demands of the calculated common address. Now, the calculated common address then basically results into this sample output value here. And of course, if it's reading, then it will expose the sample output value here instead of the exposed sample output value here instead of here. Okay, this is basically a gate which allows the external data bus to expose the value to the internal sample data bus. So with that said, all of this RAM here, then the read sample data will then need to get mixed. So because we've got independent volume control for each voice, the sample data that's being read is then modified by the common volume, and the common volume is exposed by each voice as it runs through this state machine model. And this basically here is a 64 kilobyte EEPROM. It's probably the most efficient way of doing the multiply with the sample clipping range check that we saw in the Java code. So all this does is it takes 8 bits of the sample, 8 bits for the common volume, and then produces an output 8 bits. And depending on whether or not we have the audio output enabled for this particular voice, it will output the sample data, or it will output in hex 80, which is the middle value for the middle point where the sample data is meant to be into. So because the samples are 0 to 25580 is the middle point. Now with the sample data output, because we've got 4 voices, we then need to do a final combination, and this is what these 2 blocks here do. So if I zoom in, these 2 blocks are basically identical, but they work on 2 pairs of 2 channels. Okay, so this is channel. This is one channel, and then this is the other channel. And we have here the latched sample for each voice 0, 1, 2, 3, for example. And then this is yet another EEPROM, 64 kilobyte EEPROM, to do the final sample combination step. And then the final sample value for each channel as a digital value is latched here. Okay. And what these do then is that for each channel, the left and right channel, it will then take the digital data and pass the digital data through to, this is a specific driver for the middle voltage range, because we actually want to produce a negative to positive voltage swing for the analog output. So this uses the same kind of, exactly the same IC to drive a middle value, which is again in hex 80 in hex, which is 128 in decimal, of course. And then it uses exactly the same resistor ladder arrangement here from pretty much the exactly the same IC to then produce the reference middle voltage value. And then the other channels use exactly the same kind of resistor ladder arrangement to output the different channel voltages here. And then the reference middle is then output into these, I think they're RCA connectors, which actually I'm not using the RCA connector. What I am doing is that in the final PCB, I'm only using this microphone stereo socket here. Okay, and then all of that gets combined into there, and we can see here that we've got the reference mid voltage going in onto the sleeve, and then the tip of the ring are the 2 different stereo channels. Okay, so we have the other stereo channel. Okay, so that's pretty much all of the common logic from the PCB. I also included some extra debug headers here so I could look at all of the output binary digital data, if you like. And then this is the analog debug header as well, just so I can tap that off the board cleanly, because I'm pretty sure that I'm going to have to debug this board, because this board is actually pretty huge. It's like 33 centimeters almost, so yeah, 330 millimeters, 33 centimeters approximately square. So it's a huge, very big board. You can see up here in the top right. Top right encompasses the digital to analog conversion portion of the board. It's isolated from all of the other portions. This is the 8 kilobyte, 64 kilobytes of memory laid out here, and this is the EEPROM for the common volume mixing. I'm allowing the autoplacer to actually select the position for all of the other logic ICs. And what I found was that I had to exclude some areas of the board to allow enough routing between all of the different sections, and the autoplacer pretty much places everything quite well. But this is the common logic. Now, with this PCB design tool, what I can do is that then I can take one schematic and then duplicate it X number of times for, basically it's using a sub-circuit mode, where then I can duplicate this schematic X number of times quite easily without needing to rename all of these input sources and everything. But basically, this is the schematic which handles the state and common read address calculation and all of the voice looping logic for one voice. So here we have the inputs, the common inputs for the different voice register loads. There will be 11 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, here. These are data load lines for each voice. There we go, see. And most of these data load lines, you can see here, if we trace through one of those, this one, first one here, which should be the volume, goes into this 374 latch, 8-bit latch here, okay, to read the value, and so on and so on. So you can see that it's going to be quite latch heavy, 8-bit latch heavy. And then we have the other control lines here, and all of these control lines come from pretty much the internal state machine and other areas. So we have the state machine for adding the counter and outputting the address 2. This is so that we can split the output address to expose the output address for a longer period of time while latching it for some extra internal logic later on. Okay, and then we've got a separate state for reading RAM as well. And so all of these states are used internally. We've also got some other common inputs as well for the loop mask and the active mask bits coming in. But basically, these are the inputs for the different states, and then these inputs for the different states go through all of this logic. Now, all of this logic here basically is the Java code for processing the bias and the voice. So if we look up here, say for example, we've got the voice is active mask. If the voice is active, it can read. If I highlight this, highlight the current sheet, we can see this is the voice active mask, and this is the load from the external signal from the register decoding logic. I go back to the other sheet. We can see that this is the voice active mask load signal. Okay, so if you go back to this net here, this allows us to read the voice active bit, which is exposed on the external data bus, into this latch here, single bit. And here we have the voice internal choose loop. Now this is basically reset if there's no active voice, for example. and it's set if the result of a comparison is true, for example. And this comparison here, this comparison result can, say for example, come from the result of comparing using these comparators here, whether or not the voice internal counter is greater than or equal to either the voice length or the voice loop length. And the way that we select the voice length or the voice loop length is based on the voice internal counter choose loop, which again comes from the Java code, but basically it's comparing with the selected version of one or the other value which is held inside those latches. We can see here that the logic for selecting either the sample length or the sample loop length is coming from these 2-to-1 selectors here. Now this logic in the middle is actually the internal counter logic. Now the internal counter logic is actually adding the rate to the internal position, and this is done for every tick, and this is why we're taking the sample rate latches and the values here and we're adding it. So if I trace back this by highlighting it on the sheet, we can see this is the rate low and then the rate high signal, and this loads the voice rate, the speed of playing, into these two latches here, and the output, those are used with the adders plus whatever plus the current value of whatever's in these internal counter latches. Now the internal counter value we can see here is actually quite large. It's 1, 2, 3, 4 times 8-bit latches. Actually the internal value for this 32 bits. So it's actually quite a large internal state that it's maintaining. Now don't forget that the rate value has an accuracy of 12 bits. So we're actually doing only a comparison with the last bits of the internal counter value, because we shift it down in the Java code before doing the comparison with the sample length or the sample loop length. So that's why we only have a smaller number of comparators, okay, taking the values in here. These latches here, of course, are basically coming from, I'll go back, you can see here it's the length or the loop length latches. So we're taking the loop length or the original sample length, demultiplexing it using the 2-to-1 selectors and then doing a length check. And then depending on the results of this length check, it then decides whether or not if the loop bit is also set to then do the looping logic or to kill the voice active mask. Because if we go back here and we highlight, this is the signal which resets the voice active mask. This comes from a combination of all of these different values here for whether or not it's at the end of the looping sample, and if it's currently looping or not, and if the loop active mask is set in the voice control registers. So this is actually a fairly simple schematic once you break it down into its constituent parts and understand what it's kind of doing. It's actually not too bad. This latch, of course, these ones will output the common address, and this is basically the common address for one portion of it. You can see that it's got independent output enabled. So if I look for where on this current sheet, we can see here that the common address either has the output from the address or the loop address latches, which are down here. Okay, so that's how we know that the common address is isolated, because these are only exposed in terms of output enable signals when we highlight the net on the current sheet, and the net on the current sheet comes all of this logic here, but basically where it comes from is here, which if we trace this signal back along here, up here, back down to here, it's again whether or not the address, the common address is being output to, comes from these state machine states here. And as we know, these state machine states are discrete. They don't occur in parallel with each other, they just occur in a very set sequence, so that we know this schematic, this logic diagram here, only accesses the common areas that were on the previous sheet strictly in sequence. Okay, so we know that we don't get any contention. Now, this schematic here, what I can do is that I can take this schematic and then I can paste it into these sub-circuit models here. Now, most of the common addresses and everything are, of course, identical. However, where these sub-circuits differ is that voice loop mask 0, for example, is remapped to voice loop mask 1. The active mask bit 0 is mapped to ED1 or ED2, and so on and so forth. So this sub-circuit here basically has the same schematic pasted into it. There's no need for me to modify it at all. It automatically propagates into the next 3 sheets. So this sheet is identical to this sheet, and then these 3 following sheets are also identical. The thing is that internally, the design tool will allocate new ICs for all of the different voices. And if there are any common gates, then hopefully it will merge all of these common gate ICs and stuff like that together nicely. And then that's basically the whole schematic. So what do we see or what we hear rather, when we actually want to test this schematic? So when I was running the emulated code just now, the emulated code was outputting the debug memory data bus. Okay, so now this schematic is set up to actually process that. If I start simulating the schematic, zoom in a bit, because it's quite difficult to see because the schematic's so huge. So it's actually starting to simulate now. It's simulating really slowly, of course. But basically this simulation nowhere nearly runs at real time because it's a huge board. But what I can do is that with this virtual logic analyzer, I can use it to debug these input signals here. So I can see the state machine timing, I can see the sample data and stuff that it's reading. So this is a capture. You can see the clock here, you can see the state machine signals. You can see that this little reset state machine signal here actually has a noticeable time period, and that's because of the propagation delay in the state machine reset circuitry, so that's perfectly fine. You can see here that the address and the sample data being read and everything comes through, but because it's simulating very slowly, we can see the output data signal. So we can see here that, I don't know if you remember, but the music starts off with something in the left channel, and then after about 6 seconds or so of real time, it introduces an extra instrument into the right channels. So what we're seeing here is that the left channel has sample data being processed into it, which is as we would expect, but the right channel only has 80 being output in hex. 80 in hex, 0000, but 80 in hex is basically the middle range. It's basically a silent voice, and we'll see this pattern in the simulation until the animating signal here, animated time here, goes up to about 6 or 7 seconds or so on. So I'm going to pause the recording until we get up to that point, and then you'll see that when I start the recording again, we'll see that the other channel starts coming through. So here we are now. after about a minute or so, it's got around the 6 or 7 second mark in the simulation time after a minute or two, and we should start seeing channel output on the other channel here as the other sample data starts coming along. There we go, right on time, right on cue. We saw some extra data, and then because the channel in the right hand channel goes quiet again, then it reduces back to 80, but we should start seeing the instrument playing again. Now this is simulation time, so there we go, it's started playing the instrument again, and then the instruments on that channel stop, and then it goes back to 80 again. But what this means is that we start getting debug output data from this capture device here, and we can see that on here. So if I look at the debug audio output text file, this is basically a capture of the data values that we start seeing on the input. So we've got the left and right channel. This is, I think, the left audio channel. This is the right audio channel. The right audio channel is at 80, but the left audio channel has some data into it. But this, is not easy to debug, especially when the data is really complex. When I was debugging this schematic first time around, I actually had some really, really simple sample data. Very, very known, very easy to understand values that I could trace through the schematic and actually see in the debug output. But we're playing a music file now, so the data is not going to be that understandable when we look at it in terms of a human point of view. If I scroll down quite a long way, we should start seeing the values come in on the other channel. So we can see the other values here coming in on the other channel, but we don't know what it sounds like. What we can do is that we can process this using this command here. We can process this output text file here into a binary file by chopping out the first and the third bytes, and then we can use FFmpeg to play the raw binary output file, which we processed into here. So this is the output from the binary chopping, okay, and we take the hex output, chop it, blah, blah, blah. And then we take the binary output, and then we set the sample rate to be 25,000 hertz, 25 kilohertz. We set it to be 2 channels, PCM U8 bytes. If we use this batch file, what we should hear is that we should start hearing the output audio data as calculated by the hardware simulation. So here we go. And there we are. The right channel should kick in. And there we go, the right channel has kicked in. And then that's as far as we got in the simulation, which is about 10 seconds into the sample playing. Okay, so if we go back to the simulation, we should see that we're around about 10 or 11 seconds. Okay, so that's all pretty good. If we leave it simulating for any longer, for quite a long time actually, then we should get more and more audio coming through. But this is a relatively good test to make sure that the output audio from the schematic comes through cleanly. Okay. What we can do as well is that we can, instead of doing a listening test on the output data, what we can do is that we can check the output data from the emulation, which is here. This is the emulation outputting the sample data. Okay, so this is from the Java code. And we can do a visual inspection if we wanted to with the value. So here is where the samples start playing for the music. And we can notice here that in terms of pairs, we start getting 9380, 9380, 9380, 9280. This is the right channel, this is the left channel, and it goes in these byte pairs here. This, however, is the audio data captured from the hardware simulation. And we can see here that we're getting 9380, 9380, 9380, and so on and so forth. So we can see that we're getting roughly the same kind of values. Now, the register updates compared with the emulation and the timing of those register updates is not precisely in sync with the hardware simulation register updates. Okay, so we're not going to be getting completely the same values in lockstep. They're not going to be precisely the same because the register updates are occurring at different real-time simulated time positions. But what we should get is that we should start seeing, values that we expect in approximately the correct ranges. So after a bunch of 9380s in the simulated output, we start getting 9280, 9280, 9480, so on and so forth. If we go back to the output here, we've got 9380, 9380, 9280, 9480. So we know that potentially, roughly, that we're getting the correct data. But the real proper test here would be to, of course, use this input file, save it somewhere, and use it as a golden source of data without having to generate it every single time from the emulated output. And that's what we do, is that we use this as a golden source input. Now, and because the finite state machine simulation in the hardware is deterministic, we can use this golden source of input data, run it through the simulation, and compare it with an expected data output for what we expect, because we expect the timing to be precise, and we expect the same register inputs at the same times to produce the same expected output. So this means that the golden source of data with the expected output can be automatically tested for, so we don't need to listen to the output from the simulated hardware every single time to validate the design of the hardware. We're using automated validation rather than human ear validation to check. It's just nice to listen to the output occasionally, just to really realize that it's correct. But the automated test of comparing with an expected output data is perfectly adequate for validating this design. The only thing that this digital data output model of validation doesn't finally check is, of course, the final output of the resistor ladders. And that's because when running the simulator with all of these resistor ladders, which are analog components, enabled, the simulation is noticeably a lot slower. Now, this means that these voltmeters here, when the simulation is running without all of this activated, of course, the voltages won't be correct. But I don't want to run the simulation in much slower analog mode, so I have this disabled by default. What I could do, of course, is that I could create a voltmeter which samples the voltage with the analog signals all enabled and everything else like that, but I don't do that. These resistor ladders are one of the aspects of the design which I'm not entirely sure about, so we'll just have to see how they work in reality. I mean, I am using this style of resistor ladder arrangement for the video board, and it does work reasonably well, but that was only generating positive voltages in an analog range. This is a negative to positive voltage, it's RMS voltage. So we'll see how it goes. So I'm going to be very interested to see how that works out when I actually get a PCB. This is exactly why I added all of these extra debug headers here, to give me access to the digital data plus the analog data as well, so that I can properly debug this with a scope that I have, or I can properly debug the output with the digital logic analyzer if necessary. So that's pretty much a rundown of the whole schematic. I hope you enjoyed it. Please remember, if you want to like and subscribe this video and add any comments or questions or suggestions that you may have. I'm always very happy to receive feedback from these crazy projects that I do. Thank you very much.